Okay, good evening everyone. Welcome back to the NPTEL live video sessions. This is week 11. So in this session, we'll be discussing about how to solve the indeterminate structures using the moment distribution method. So far, if you remember, in the last few classes, we were discussing about structural analysis of indeterminate structures. First, we started with the flexibility method. So flexibility methods makes use of the compatibility equations. So using the compatibility equations, we try to solve the unknown reactions, like the redundant forces. After that, we moved on and we tried to use slope deflection equations in the last class. So in the last session, we tried to formulate the slope deflection equations, and we try to solve again the unknown redundant forces, along with also some of the degrees of freedom, like the rotations and also the joint rotations, and also if there is a sway, we also try to find out the sway in the frames. So in this video session, we'll be discussing about the moment distribution method. This is also one of the method. This is mostly an iterative method, so we'll keep iterating it until we try to uh, until we obtain the solutions at certain level of accuracy. So this was first developed by the Hardy Cross. This was developed by Hardy Cross around 1930s. So this is also one of the famous methods in the structural analysis. So uh, before we start solving this questions or solving the problems in using moment distribution method, we just touch upon some of the concepts involved in moment distribution method, so that it will be easy, and also it will also have some continuity in our problem solving sessions. So if you remember, last time we were discussing about the movements, right? Last time, if you see, again, in all the methods, always we assume that even though if the real beam or the real structure is having some pin or the roller supports, we initially assume it as fixed supports, and then we release the moment from it, and then we'll be finding out how the moments are distributed, right? So similarly, if you remember, last time we were discussing about the the moments. If the far end is fixed, and if we have an hinge support, and the far end is fixed, and let us say uh, I have applied a moment m, and this is clockwise always. In even in the slope deflection method, we were taking clockwise as positive, and downwards displacement as positive, if you remember. So again, I'm applying a clockwise moment. So what happens if I apply clockwise moment? It will deform in such a way, okay, and this will be theta. Okay. So in the last session we have derived these things, right? So this is, let us say this is A and this is B. I'll call this as MAB, and this is MBA. Okay. So if you remember, we have derived what is MAB in terms of theta. What is it? 4EI by L. So this is, the span is L. 4EI by L times theta. Okay. Similarly, we also derived for MBA. MBA is nothing but, again, you'll generate a clockwise moment, which is 2EI by L times theta. Okay. So now let us just move a step forward, and we let us define. Let us actually define what is a member stiffness or a member stiffness factor. So usually how the stiffness is defined. Stiffness is defined as load per unit displacement, or also the moment per unit rotation. Okay. So what happens in this case? So let us say if my MAB by theta is nothing but 4EI by L. You take it from the top. Okay. Okay. So for a unit rotation, let us say when theta is unity or one, what happens? Then MAB is nothing but the stiffness. I call it as K. So stiffness of that member is 4 EI by L. So what does this mean is if you apply a moment of 4 EI by L at support A, so you will obtain a rotation theta which is equal to 1 unit or 1 radians, whatever it is, 1. And also it will induce moment. You'll also get a moment at the fixed support, right, which is at the far end. So this will induce a moment of 2 EI by L. Okay, that is what it means. So we from now onwards, let us call it as stiffness K. K is nothing but again the moment per unit displacement or unit rotation. So now this is about the stiffness. So once we obtain the stiffness, next, what if we have a joint? Okay, what if we have a joint in? Let us say if you have a T joint like this, and this is fixity and this is fixity, and you have again fixity. Okay, if this is a joint, what happens here? A, B, C, D. Now, how do we use again? How do we make use of this stiffness K that is equal to 4 EI by L? And mind you, this 4 EI by L is only when the far end is fixed. Okay, we'll see what happens if the far end is hinged. Okay, so let us say I'm applying a moment M at the joint uh, B. Now the joint B is an intersection of three members. Okay, A B, B C, and B D. So if I apply a moment M at the joint, now each each members will actually divide that which will divide that moment M, right? So how it will divide? Let us say M is nothing but MBA plus MBC plus MBD. So this is how this M will be divided in between. So in what proportion it is divided? That again that is the question, right? So because why do we know, why should we know in what proportions it is getting divided? Because if you solve MBA, for example, if you solve MBA, so now let us say this is A, and let us say my MBA is something like this. If you can solve for MBA, now you can simply solve what is happening here, right? So this will be like MAB. This can be solved because once you know about this is a cantilever, and you have you know what is going to happen here. So at the end, again, our main aim or main goal of structural analysis is to find out the internal forces by finding out the support reactions. Right? So this is our main aim, right? So that is the reason why we need to find out what is MBA, MBC, and MBD. So to find out MBA and MBC, we should know in what proportions they are actually getting distributed or getting divided. Okay, so this is again how can we solve for this? So we know that theta rotation here, right? So let us say if it is rotating something like this. Okay, so there might be rotation like this, and let us say it is rotating like this. Okay, we have something like this. So as per the definition of a rigid joint, what is it? Like what's the definition of a rigid joint? So after the rotation, the angles between the joint angles between each member will be maintained, right? If it is 90 earlier, it will be 90 even now. So if that has to be maintained, then the theta should be same. So let us say this is theta BA, and let us say this is theta BC. Let us say this is theta BD. So for a rigid joint, for a rigid joint, theta BA should be equal to theta BC equal to theta BD. Okay. So I'll write it as theta. Fine. So once we know if it is theta, then we already have this equation M equal to MBA plus MBC plus MBD. Okay. So what is M in terms of stiffness? Like just now we have defined what is K times theta is M, right? Stiffness times theta is m. So for unit it is for a unit rotation it is called moment. But if you have some theta rotation, then you need to multiply the stiffness with the theta. It is something like this. So you have P is equal to k times delta. So similarly, we have M is equal to MBA. Then what? Stiffness of BA times theta. Theta BA, but theta BA it's already theta, so that's why I'm just writing as theta plus K stiffness times of BC, stiffness of BC times theta plus K BD times theta. Then what is M? M is my total stiffness. I'll write KT of theta. Okay. So once I have found out my this KT, I'll just cancel down this. Okay. So KT is nothing but KBA plus KBC plus KBD. Okay. So how can I write that again? I can simply say that K what is it? So let us say if I want to find out MBA, okay, MBA is nothing but this is KBA times theta, right? MBA is nothing but KBA times theta. But what is from this you can just simply say that M BA can be found out or how it is distributed. This will be in terms of KT divided by KBA plus KBC plus KBD. Sorry, K. If you want to find MBA, then it is KBA plus KBA times M. Okay, so you can just simply find, for example, if you want to find MBA, then that is actually uh, it is again in proportion of KBA. The stiffness will be so the moment which is distributed into each member is actually distributed proportionately or directly, or it's directly proportional to the stiffness of the member. Okay, so what again now comes the distribution factor. So in this how it is distributed, again distribution factor is you have total moment m, but how are you going to divide this total moment m into each member? So that is what the distribution factor is. So we call this as distribution factor. So distribution factor, let us say for each member that is going to be distribution factor for let us say we have three members here. So I'm just writing it as I, any member 1 2 3. I is actually 1 2 3. So that is actually going to be Ki of that member divided by Kt. Kt is nothing but the total stiffness. Total stiffness is the summation of all the stiffnesses. So this is what the distribution factors are. Okay. So why do we need to know the distribution factors? Because we need to know how the moments are distributed between each members. Why do we need to know why the moments are distributed in each members? Because we want to find out the support reactions or what is going to happen at the far ends. Okay. If you want, right now we have a far end which is fixed and it's actually the support. So once we know what is happening in that member, how much the moments are distributed in that member, we can find out the support reactions. We can find out the reactions in the supports which are located far from that joint. Okay, so this is one more point. So this is again distribution factor, which is Ki. So each distribution factor, the distribution factors are directly proportional to the stiffness of the members. Okay, and yeah, so far we discussed about the stiffness. What is the stiffness factor? So stiffness factor is nothing but the stiffness of the member. So we have derived 4E by L, and you need to keep this in mind that it is for the far end fixed. And we also learned what is the distribution factor. Distribution factor is nothing but how the moments are distributed when you apply a moment M in the joint. How the moments are distributed in each members. That is one point. And the next one will be the carryover factor. So what is the carryover factor? And why are we learning all these things? And maybe once we start solving some problems, I think it will be more clear. So what is carryover factor? So the carryover factor is like, let us say again, let us suppose I have the same thing. So pin support. See, the reason why I'm actually applying a pin here is see, pin supports generally rotate, right? That is the reason why I'm showing a pin. Otherwise, I can even show that my fixed support has rotated. Maybe there is some settlement, some rotation in the support, something like that. But anyways, let me just stick on to the pin support. So pin support I have. So I'm just rotating it. So I'm just rotating it something like this with moment m and theta. Again, I'll suppose theta is 1 for now. Okay, for time being. So what is m? We already found out what is m. M is nothing but 4ei by L. Okay. Now, if you apply m moment here, what is happening here? M, this is A, B, this is MBA. MBA is nothing but 2ei by L. That means half of the moment is shared. This is half of M. Okay. So what happens is that if you have a if you have a a fixed support, and if you are applying so if you have a fixed support and you are applying moment M, it will carry the other end or the other part of the support will take m by 2. Okay, so the carryover factor is generally half in this case. Okay, and if you, for example, if you have a pin supports and if you are applying m, then there is no carryover here. The moments are always zero, right? At the pin support, the moments are always zero. So m is zero here. I'll call it as m dash. M dash is zero. So in this case, it is zero. Okay. So this is one concept. We have discussed about stiffness factor. We have discussed about the distribution factor, and we have discussed about carryover moments. So the main theme or the main the important uh, concepts of the moment distribution method is, so in this what we'll try to do is we'll try to do successive approximations. Like we'll initially assume that everything is fixed. Okay, and then we'll find out the fixed end moment. So last time I have already derived or already formulated the fixed end moments, right? For a fixed beams, if you have UDL, what is the fixed end moments, and if you have a point load, what are the fixed end moments. So we'll have the fixed end moments, and then what try to do, we try to, if there is a pin support, so we'll try to unlock it. For initially, we'll assume it as a fixed support, and then we'll try to release that moment. So we'll get some moment. We'll apply the same moment in opposite direction, so that it will be released. Releasing is nothing but that we don't have any moments there, and bend moment there is zero. So we'll try to release it, and then because you are releasing it where you have a fixity, there you will have a carryover, right? So you will have a carryover moment there. So we'll try to add it, and we'll try to do successive iterations until we get some significant accuracy, or maybe we'll match up to some decimals. And then once we will try to get some approximations, and we are when we attain some kind of an accuracy, then we'll stop these iterations, and then we'll present what are the results. So this is again the concept behind how we are going to solve how we are going to solve for the redundant forces using the same moment distribution method. So let us directly start solving one problem. So once we solve the problem, I think things will be more clear. So let us so so we have a continuous beam. Let us so we will solve two different types of problems. One will solve a beam problem, and then one we solve a frame problem. And in the frame problem, let us solve for the sway condition. We will also allow for the sway, and then we'll see how can we solve the frames in sway conditions using the moment distribution method. So let us first take this question. The question is something like this. So we have a continuous beam. Okay, this is a continuous beam. Both the ends are fixed, and we have a roller support in between. Okay, so this is a roller support, and we have a roller support somewhere here, and then yeah, okay. So we have a UDL in the midspan. Oops. UDL in the midspan, and then sorry, this is not the midspan because the lens are not the same. UDL in the span there, and then we have 250 kilonewtons point load. Okay, this is A, B, C, D. Okay, and when coming to dimensions, this is 4 meters, 4 meters, 12 meters, and 12 meters. Okay, so obviously this is an indeterminate structure. Like we can't simply use our equations of equilibrium, uh, and we can't directly solve such a kind of question. So again, the loadings are unsymmetrical, so we can't simply assume that we can just if that is symmetrical, we can just take half of the section and then the other half will be the mirror image of it, right? It will be similar to what's happening in the first half. So this is not symmetric. This is not a determinate structure. So let us solve by using the moment distribution method. Okay, this can be uh, as already we have solved this using different types of methods. Like the last time we have used flexibility methods, and the previous session we have used slope distribution methods. So now we'll start with the moment distribution method. Okay. So again, in moment distribution method, usually we follow some kind of a tabular format so that we try to not make mistakes. Okay. Once we have everything detailedly, presented in kind of a tabular form, it will be very easy for us to actually carry over those steps to each other step, so that we will not make any mistakes. So again, what are the important things we need to initially have beforehand solving this moment distribution method? So initially, let us take EI as constant always. So in this EI is constant, and the lens are all the things are in meters, and UDL is 20 kilonewton meter. Okay. So what are the first few things which we need to do? First few things are, first we need to find the stiffness factors. So the stiffness factors, again, what we assume everything is fixed. Okay. So everything is fixed. Obviously here the obviously in this problem everything is fixed. So let us first find what is stiffness of AB. What is the stiffness of AB is nothing but K 4EI by L. Let me write L 4EI by 12. So this is going to be EI by 3. Next KBA is also the same. So this is nothing but KBA for the same. KBC is going to be 4EI by 12, and this is also the same. KCB is same. Okay. So stiffness of KCD is going to be 4EI by 8. Okay, here this is 4 plus 4. So this is going to be EI by 2, and KDC is also equal. Okay, this is similar to this. Next, distribution factors. So distribution factors. Why do you need to have the distribution factors? Because if see right now what we are assuming is, let me just use some more sketch. So what we'll assume is, we'll assume that everything is fixed here initially. Obviously, A and is already fixed, so there's nothing to assume there. So first we'll assume that BC are fixed. Okay, and then we'll try to obtain the fixed end moments. So once we obtain the fixed end moments, there has to be, see, B and C are actually the continuous supports. Those are not the fixed supports, right? So the difference between the fixed end and fixed support and the continuous support is, if it is a fixed end, what happens is that you will only have FBC, or sorry, or MBC. Okay, you'll only have this moment MBC. So MBA is 0 if it is fixed. Okay, but for the continuous support, MBC should be equal to MBA, and it should be opposite. Okay, so those things we have seen last time. If you remember, we tried to write the compatibility equations, or the extra equations other than slope deflection equation. So we assume that it is sorry, not assuming, we try to write down an extra equation saying that MBC plus MBA is equal to 0. Alright. So what happens in this? So once we have found out what is the stiffness factors, next step is to find out the distribution factors. So distribution factors comes at the point of, see, there's no nothing to distribute between A B, right? Because A itself is a support, so there's nothing to distribute among A B, because whatever you apply at A, it will carry forward. That M A is nothing but M A B. So we need to find out the distribution factors at the point of at the common points, or at the joints. So here the joints are B and C. So distribution factor, sorry, yeah, distribution factor at let us say what is distribution factor of BA. Distribution factor of BA is going to be stiffness of for now I'm just writing stiffness of BA by my total stiffness at that. So its total stiffness is nothing but KBA plus KBC. Okay. So stiffness of KBA is nothing but EA by 3 divided by KBA plus KBC. How much is that? Same. So 2 by 3. So this is going to be 1 by 2. This is 0.5. Distribution factor of BC. See, and you need to understand distribution factor at the joint is equal to 1, right? Because DFBA plus DFBC, DFBA plus DFBC is nothing but KBA by K total plus KBC by K total. So that is nothing but KBA plus KBC is nothing but K total, K total, K total, that's going to be 1, unity. So distribution factor should always be unity, so that will also be a cross check for us. Anyways, here it is quite straightforward. So distribution factor for BC is 0.5. So what does this 0.5 mean? So if you apply a moment M, some M, external moment, I'm not saying about the internal moment for now. So if you apply moment M, so MBA is going to be M by 2 and MBC is going to be M by 2. So that is the concept behind the distribution factor. Okay. Next step is going to be okay. We need to find the distribution factors for the next joint, that is joint C. So DFCB, distribution factor of CB is going to be KCB by K KCB plus KCD. KCB plus KCD. And KCB is going to be how much? EI by 3. And KCB is EI by 3 again. KCB is also EI by 3. It's EI by 2. So EI by 2. So how much is this going to be? 1 by 2, 0.33, 0.5. I think this should be 0.1 by 3 by 1 by 3 plus 1 by 0.4. Okay, this is 40%. So KF, um, what is the other one? KFCB, we have found out KFCD. KFCD is KCD by KCB plus KCD, and this is going to be 1 minus 0.4, or EI by 2 by whatever that is. This is going to be 0.6. So we have found out the distribution factors. What is the next one? Carrier moments is the carrier factors are half all the time, so there's nothing to find out there. But the next important step is to find out the fixed end moments, FEM. Last time we are discussing about the same things, right? So fixed end moments, FEM, fixed end moments. So in AB there is no moment, external moments acting, right? So the fixed end moments are zero. That means MBA is zero, MAB is zero, and M in BC we have some external moments 20 kilonewton meter per meter acting, right? So fixed end moments of MBC is going to be minus WL square by 12. The reason why minus is we have a fixed support and we have M acting like this, and the moments will be WL square by 12 and WL square by 12. So this is clockwise, that is why positive, this is anti-clockwise, and that's the reason why I'm taking it as negative. So W is 20, L is going to be 12 times 12 by 12. So this is minus 240 kilonewtons. Minus 240 kilometer. Okay. Similarly, FEM, CB is also the same. FEM CB is plus, but plus 240 kilonewton meter. Okay. I'm just for the completeness, I'm just writing all the other fixed end moments here itself. FEM CB is 12 and FEM CD we have a point load at the midpoint, right? So it is WL by 8. So remember it is WL by 8 or PL by 8. So FEM C FEM CD is minus just let me write PL by 8, that is minus 2 250 by 8 by 8. Okay. Now maybe you might have understood why I have taken length as 8, so that it will be easy for calculations. Anyways, minus 250 and FEM DC is going to be minus PL by 8, that is minus 250 times, sorry, this is plus 8 by 8, so this is 250 kilonewton meter. Okay. So we have obtained the fixed moments, we have obtained the distribution factors, and we know what is how we also know the carryover factors, and uh, we also know the carryover factors, and we also know what are the supports. Okay, what are the support conditions. So now I think we are ready. We are ready to start solving using the moment distribution method. So again, we have different types of formats. So I just use a simple format. We'll initially start with we'll start with the joins. So we have join. So what are the joins? Joins are the nodes. Nodes are A, B, C, D. So joint, and we have members. So each joint will be actually each members will actually uh, converge at the joint, right? Or will meet at the joints. So we have for joint A we have only one member which is meeting, right? Because there's nothing which is adjacent to, or A itself is a support. So next for joint B we have BA, and we also have BC. Okay. For joint C we have CB, and we have CD, and for joint D we have only DC. Again, just for completion. So this is the question. A, B, C, D. A is a fixed support. B, C are the continuous supports, and D is my again. D is also a fixed support. So this is how I have defined my joints. Let me just draw it little clearly so that yeah, there is nothing here. So I'll just erase it so that I can use it for some of calculations. And this is A, this is C, this is D. So we have BC and CB. Okay. Now, first, let us just write what are our distribution factors. Okay. So we have distribution factor. So for AB it is zero. There is nothing, right? It's you don't have any distribution happening in AB. So for BA it is zero point 0.5. For BC it is zero point 0.5. We have just solved it. So for BA it is zero point 0.5. For BC it is zero point 0.5. For CB it is zero point 0.4, and for CD it is zero point 0.6. Okay. CB it is zero point 0.4 and CBD it is zero point 0.6, and DC there's nothing happening at the joint there. Okay. Now fixed end moments. First let us write the fixed end moments. So this is where we start solving for the moment distribution methods. So fixed end moments, again let us go back and just see what is happening in the fixed end moments. So fixed end moments, BC is minus 240, CB is 240, and CD is 250 and 250. Okay. Uh, BC is minus 240. Okay. CD. So all in this again, I'm just not writing units. So you please assume it as kilometer meter. So CB is again 240 positive clockwise. CD is minus 250, and DC is 250. Okay. So this is my fixed end moments. All right. So now we once we obtain these fixed end moments, so these are actually distributed, right? Like once we have these fixed end moments, what happens? Now we have actually given a moment of minus 240 in BC. Okay, so what happens in CB then? So we have given a moment of, let us say in this we are given a moment of minus, this is minus, right? Okay, this is minus 240. So this will actually use a carryover, it will carry over here, right? So in minus, this is also minus again. So this will carry over as 120 in the same direction. So now first let us write our carryover moments. So I'm just writing carryover as C. Let us write it as carryover for first time. Carryover moments. So what happens is that my BC will carry over here as minus 120 and my CB will be carry over here. Okay, as okay first no, oh sorry, okay, the carryover should be okay. Just a second, I just made a mistake. Okay, so see, first we are applying minus 240, right? So that minus 240 is actually in BC, right? So because of this minus 240, uh, it actually have a carry over towards what? Like see, BA is not having any moment here. So BA is not having any moment. That means the minus 240 we are applying at the joint, right? So if you apply the joint, BC should the same moment should be divided between BC and BA, and in what proportions? It proportions of distribution factors. So right now it is minus 240. Then you should have an equal and opposing forces of plus. So what is my distributions? So distribution or the distribution distributing forces. Okay, the distributing forces or moments. So this is going to be, this is minus 240. So I need to apply a plus 240 times zero point 0.5. That is going to be 120. Okay, and the same thing. So you have 240 which you need to apply in a opposite direction, and that is going to be 120 here and again 120 here because it is zero point 0.5 and zero point 0.5. So same moments are going to distribute here. Fine. What is the next step? Next step is to apply similar thing. Again, you have 240 here. So 240 is going to be distributed. How much is going to be distributed? The distribution will be, so we have CB, which CB is, yeah, CB is going to be 240. So this is 240. So we need to apply a minus 240, which is uh, that is going to be minus 240 and minus 240 times zero point 0.4. How much is that? 240 times zero point 0.4 is 24, 16, 96. So we need to apply minus 96 here. Okay. And what is going to happen in this? I think I'm making some mistake here. CB you have and CD. Just a second, I think. Okay, all right, yeah. So first let me go back. So we have this support B, we have support C. Okay, let us first see what is happening at the support B. In support B, MBC, we have already derived MBC as minus 240. Okay, at support CB we have plus 240 and minus 250. How much is that? So we have, see, in support C, we have plus 240. Let us say this is my support C. Uh, this is my support C. Support C, CB is going to be positive 240 and CD is going to be, is it negative? Yeah, it is negative. Negative minus 250. Uh, Positive, this is positive 240 and negative, that is going to be the the net moment in the joint is going to be minus 10, right? So if that is minus 10, I need to apply plus 10, plus 10 clockwise 10 here, right, to unlock the moment, or to actually make the movements, to actually negate the movements. So I need to apply a movement of 10 in positive direction at that joint. So if I apply a positive movement of 10 at that joint, my CB is going to get a share of 40% of it, because my distribution is zero point 0.4. Okay, so my distribution is zero point 0.4. So I'll just write it in. So the net is minus 10. Okay, so if the net is minus 10, I need to apply a positive moment of 10 kilonewton, 10 kilonewton meter, and that 10 kilonewton meter, I'm trying to apply it at the joint. Okay, so once if I'm applying 10 kilonewton meter, CB will have some shear and CD will have some shear, right? So CB share is zero point 0.4 times, because the distribution factor is zero point 0.4 here. So we'll get the distribution has 4 here. Okay, so what about CD? CD will have plus 6. All right. Now what is going to happen at BC? So BC, the total net at B is BC only, because BA is not having any fixed. So let me write 0 here. Yeah. So BA and AB is not having any fixed end moments. So BC is only having a share of minus 240, and minus 240 has to be shared by BA and BC. So plus 240, actually, plus 240 I need to apply it, so that I'll be unlocking my moments there. So if I'm unlocking moments 240 there, it has to distribute a moment in BC as plus 120. Okay, and here it is plus 120 again, because you have 50% share between BA and BC. Okay, so this is plus 120 and plus 120, 4 and 6. And next what is going to happen? So once we have this, and this will also be carried over, right? Because now each, like, I'll take again the same condition C. In C, now what is going to happen is CD is having a positive moment, this is clockwise, of 6, and CB is having again a positive moment, which is again clockwise, right? So yeah, this way. Sorry, oops, clockwise, and this is clockwise. Okay, this is 4. Okay, so 6 we have in CB, CD, and 6 and 4 is in CB. So because of this 4, you'll have a carryover factor of 2 in BC, B, C, and D. So because of the 6, you'll have a carryover moment of how much? 3. It's half, right? So what I'll do is, for the carryovers, what I'll just simply write is, because of CB, because of CD, sorry, CD, I'll have 6, and that will induce net force, or the net moment of 3, plus 3, because of the carryover in C. So right now again it is unbalanced. You can see at joint C, it is 4 and minus, sorry, it is 4 and 6 here. So it has to be equal, right? So now it is balanced. So we need to keep iterating. So in DC we'll have a carryover of zero point 0.5, and DC will take a moment of 3 here, and 120 in BC also. Similarly, we have, this is A, this is B, and this is C. Now we have BC. How much we have? We have a positive movement of 120 here. And in BA, how much is it? Again, it is positive movement of 120. 120 means this is 120. So because of a positive movement of 120 in BA, it will induce a carryover of 60, and this will in turn induce, because of BC, which is 120, it will induce a carryover movement of 60 in CB. Fine. So BC will have a carryover factor to CB, which is 60 plus 60, and BA will induce a carryover factor to AB, which is again plus 60. Let me write it as carryover moments. Okay. So once we have this carryover moments, next this will be again distributed. So how this is going to be distributed? So distribution is going to be now just now just add on uh, add each terms in it. So we have CB is going to, where is CB? Yeah, CB. So we have CB, right? So CB is actually inducing a carrier of 2 here. So I need to mention 2 here. Plus 2. Fine. And did I miss anything? 6 is carried over to 3, 4 is carried over to 2, 120 is 6, 120 is 60, and 120 is 60. So next, how is this going to distribute? So we have 2 here, we have 60 here. That means at joint B, now we have only 2. 2 is my 2 is my uh, net moment there. So I need to distribute minus 2 in the at the joint B, and if I apply a minus 2 moment at joint B, that BC and BA will take the share equally, right? So this will actually have a distribution. Again, I'm writing the same step which I have mentioned above. So this is going to have minus 1, minus 2. So minus 2 is again minus 1 here and minus 1 here. Fine. And here I have 60. And in CB I have 60. And CB is this thing, and CD. Do I have anything in CD? CD is nothing. Yeah, CD I don't have anything. So 60, that means I need to apply minus 60 at joint C. So if I apply minus 60 at joint C, the CB will have a share of 40% of it. So 60 times 40 is 240. So 60%, right? So 40%. So 40 is zero point 0.4 times 60, it's 24. But this is minus. And here you have minus 36. Next, what do you need to do? You need to just again simply carry over it, right? Because now you obtained moments in each member, so then it will be carried. So this will carry as minus 18, okay, and this will be carried as minus 12, and this will be carried as minus zero point 0.5, and this will be carried as minus zero point 0.5. So this is carryover moment. Now once we have carried over, again we need to distribute it. Okay, so now why we are actually distributing it? Because at the support we are not able to achieve uh, the same or the equal number of or the same bearing moments, right? So in this, what is going to happen? We have again joint B. Where is joint B? So we have BC and CB. Okay, so we have BC and CB, which is a joint C. BC and CB. This is not the one. So BC and BA. So what is happening at BC? BC now it is 12, minus 12, right? So minus 12, I need to apply positive 12 moment. So if I apply positive 12 moment, what is how is it going to distribute? 5, 12, right? 12 by 2, which is 6 and 6. So plus 6 in BC and plus 6 in BA. Okay. And here, CB I have only minus zero point 0.5. So I'll apply only plus zero point 0.5. So if I apply plus zero point 0.5, it is going to distribute as 5 plus zero point 0.5. So this is going to be 0.2. Okay, zero point 0.2, and this is going to be 0.3. Now again it will be carry over. So you just carry over this to this. This is plus 0.15. Fine. And this is going to carry over to zero point 0.1, and this is going to be 3, and this is going to carry over here as 3 again. Next, once it is carry over, see at the end what we need to get is the carryover moments, or the carryover should be almost nullified or almost the same, or almost zero. There shouldn't be nothing. There should be anything to actually carry over. Once we have nothing to carry over, that means the joint rotation, the what do you call, the force equilibrium equations, or the force or the equilibrium equations are satisfied, right? So once we have this distribution, again let us go for the next step of distribution. So in BC we have zero point 0.1, right? So I need to apply minus zero point 0.1. Okay. So if I apply minus zero point 0.1, this will get a share of minus 0.05, and this will be minus 0.05. And what happens at this point? So we have 3. So I'll apply minus 3 here. So if it is minus 3, see, I need to apply minus 3 rotation to nullify that carrier factor of 3. So if I'm applying minus 3 externally at the joint C, this will distribute, it will be distributed in terms of 40% and 60%, right? So 40% of 3 is minus 1.2 and 60% is minus 1.8. Fine. So now again it will be carryover. We'll have a carryover. So you have a carryover again. So carryover again. This will be carried over as minus 0.025. This will be carried over as again minus 0.025, 0.025, and this is minus 0.6, and this will be minus zero point 0.9. Fine. Next, what is our next step? Again, next step is distribution. How much is again distributed? So now we have minus 0.6 and minus 0.025. Okay, so we have minus 0. We have a moment at B in BC as minus 0.6. So we need to apply plus 0.6 externally. So if we are applying plus 0.6 externally, the distributed moments will be zero point 0.3 and zero point 0.3 here. Okay, and when you have minus 0.025 here, right? So if you have minus 0.025, you need to apply plus 0.025. So again, that will make a distribution of 40 and 60% in this. So 40% of 0.025, 0.001, 0.01, and this is 0. This is 60%, right? 12 6 are again this is 0.015. Okay, and there's nothing here. So once you obtain this, now right now we have distributed this. Now we have see we have nothing to see. As we go down, right? Again, now it is actually getting into decimal places, point zero, point zero, point zero one. So we, if we keep on doing that things, right? So this decimals will keep vanishing. So it will keep on going to almost equal to zeros. So we started with something like 120s or something like that, right? So the fixed movements are in terms of 120s, and we are getting up to the decimals of point 0.3. So you can still go further for the one more step, but let us just stop it here and we'll see what are the final moments. So how to find, again, the important step is what is how to find my final step. So final movements. So final movements are nothing but you need to just add each column. So you just add each column. Okay. So if you add all these things, 60 minus zero point 0.5 is 59.5 plus 3 is 59.5 is 62.5. So 62.5 minus 0.025, I just don't want to care that. So it is 62.5. And what is going to happen at BA? BA is 120. And mind, you need to not add this thing. Okay, these are distribution factors. These are not the moments. So 120 minus 120 minus 1 is 119. Plus 6 is again 119 plus 6 to 125. 125 plus 125.3, right? 125.3, something like that. And similarly in this again, it is minus 240 plus 120, it's 120, 122, 122, 121, 121 plus 6, 127, 127, uh, 127 minus 12 and minus 6, then plus 3. So this is going to be minus 120, minus 125.3. Okay, and then 240 plus 4, 244 plus 60. 244 plus 60 is again what is this? 64, 304 minus 24 plus 3 minus 6. So this will be around 281.5. Okay, and this is again minus 281.5, and this is 234. Let us just yeah, 250 minus 253, 250 minus 18, 232, 235, 235 minus zero point 0.9 plus 1. This is around 234.3. Okay. So two things. One, either you can stop when you have the same these things. Okay. When you have same BA and BC, and also when you have distribution is very lesser. Okay, so why very lesser? Because once you keep on carrying forward, right? So once you keep on carrying forward, the same decimals are actually getting accumulated there. So there's no point in keeping it iterating it further, because the movements are in terms of three decimals, not three decimals, the 120s and hundreds, right? So it is better you stop at the decimal point of maybe like point 0.3 or point 0.5 or something like that. So once you find out, so this is from this what you are actually what is it actually what you are actually getting is. So let me draw a beam, again the same question. So we have this support, we have continuous supports. So this is my 250 kilonewton, and this is my 20 kilonewton meter, A, B, C, D. So from this what we are obtaining is, when I say MAB is 62.5, that is it's in clockwise direction, 62.5. Okay, and MBA, MBC, again it is again you cannot simply just write it here. It's better you draw a free body diagram and then you say it. Maybe we'll do that in while we are drawing the bending moment diagrams. So MDC is again clockwise, 234.3. Okay, so this is what it is. So how to find the shear forces? Shear forces are again simple. You need to just break down each thing. You need to find the free. You need to just draw the free body diagrams. This is 62.5. MBA, you obtain it as again positive 125.3. Okay, so if this is positive, you need to have a negative moment, which is actually countering it. So you should have a positive shear force which is applied upwards. So this is going to be 125 plus 3.3 by this by L. So this is nothing but 15.6 kilonewtons. So if this is upwards, this is downwards, because there is no in between forces, right? There's no external forces in that span. So this is going to be downwards. Similarly, you can find out what is happening at B and C and D. Okay. So I'll just write down the complete. Let me write down the shear for complete bending free body diagrams. This is 62.5 and this is 15.6 kilonewtons, kilonewton meter, and this is 125.2 kilonewton meter, and this is 15.6 kilonewton meter. Similarly, you can write for this is 107 kilonewton, and this moment you already know, this is 125.2, and you have a UDL in span BC. So this is going to be 133 kilonewton, and you have a clockwise movement. In CB, it is a clockwise momentum, 281.5 kilonewton meter, and then A, B, B, C. You have CD, right? You have C and D. So this is 250 kilonewtons. So this is going to be 130.9. You can see here. One is it 130? No, this is 281, right? Minus. So this is going to be, this is 281.5 kilonewton meter, and the shear force is 130.9. And what about DC? DC, we have found it out. DC is 234.3 positive. That means clockwise. 234.3 kilonewtons. So you have 130.9 acting here. So it should be 119.1. Only then both will be equal to 250. So you should try to draw the bending moment diagram. Let me just draw the bending moment diagram quickly. So yeah, first one is 62.5. Let me draw it. Let me draw on the tension side. Okay. So this is going to be, yeah. So this is 62.5. All okay. and then at B it is again on the top wards, and that is 125.5. So what I'll do is at B it is almost twice. So this is something like this, and this is going to be linear. Why it's linear? Because there is no force acting in between the span AB. Okay, so this is I'll just label it once I'm done. So yeah, this thing, and yeah, we have a UDL in span BC, so we need to be very careful while drawing the UDL there, right? So here it is 125, that is fine, and at C it is 281.5, so that is again at the top. Okay, there is a hogging moment coming there. That means it will start again the same place, but it will be a little higher. That is 281. Okay, and it should be parabolic. So you can actually you can actually see at the mid span that this is going to be positive. Okay, the mid span, the bending moment is going to be positive. That means it is actually going into a double curvature. So what I'll do is I'll just try to draw a, assume this as parabolic. Okay, so this is how it is, and after that we have what do we have? So we after that we have a unit load of 250, sorry, point load of 250 kilonewtons. So if you have point load of 250 kilonewtons, how is this going to how is it going to change? So we have point load of 250. So this is having at D. What is going to happen at D? At D it is again, oh, it is again positive, right? It is going to be at the top. So if it is going to be at the top, fine. So if it is going to be at the top, then yeah. So it is 231. So far we obtained this is around 281. Okay. So this should be around 231. At B it is 231. So this is 231. So we have something which is at the middle, so that again you can find out what is happening at 250 point where the point load is happening. So if you find out, you can just you'll be getting a value of 241, which is positive. So this is going to be hugely positive. So somewhere here. So this point it is going to touch like this, and then it is going to meet the point something like this. The reason why it is linear, because there is only a point load which is acting with, at the mid span of span BC, span CD. So I'll just label it. This is 62.5, and here it is 125.2. And this actually I did not calculate, but you can just cross check. This is 160.9. Okay, this is 281. Okay, and this is going to be we already know about this. This is 234.3. So whatever upwards I have considered as hogging, right? So yeah, positive, positive, positive. Okay. So this is about the bending moment diagram. So yeah, any doubts in this question? Maybe we can discuss.
Uh, when we're taking this distribution factor for BP,
Yeah.
so the other end is spin. Why we are taking it 4 by L?
BC, right?
Yeah,
For
BC.
BC. Yeah, yeah. So that's what. See, like in BC, the other end is pinned, right? But in this question, uh, what we are trying to do initially is we are assuming that everything is fixed. All our supports A, B, C, D are fixed, and then we are trying to remove that fixity there. So we are applying. See, if you see in
Okay.
this, we are what we are trying to do is we have a net movement here. Where is that? So uh, 3 is my moment there. So I'm applying, my net moment is 3. So I need to apply minus 3 to remove that fixity. So when I'm applying minus 3 to remove that fixity, that will induce, that will distribute the moments as 40% in BC and 40% in CB, something like that. So
No,
in
no,
this
I'm talking about the initial calculation of distribution factors.
yes, yes, that's what. So initially, what we are trying to do is that in this concept, we'll try to assume all the supports are fixed initially, and then we'll try
Okay.
to lock and unlock, lock and unlock, lock and unlock, and until the point where we'll get see at the point C it is actually a roller support, right? So it's a continuous support. So we try to do this locking and unlocking at the point where we'll get MCB plus MCD is equal to 0. That means there is no net movement in that.
Okay.
So that is the reason why, see, for if you see here, the reason why I'm applying how see here, you can actually you can appreciate this. So you have CB and CD. So because of fixed dead moments, CB is giving me a moment of plus 240 kilonewton meter, whereas CD is giving me a moment of minus 250 kilonewton meter. Okay. So, as per our knowledge, as per our so far whatever we have learned, at the continuous support, moments should the net moments, that means MCB plus MCD should be 0. As we are assuming it as a fixity there, we are not getting 0 because 240 minus 250 is nothing but minus 10. So we have a minus 10 which is actually lying in the system where we are not able to try to iterate it out, not able to find a solution for it. So what we try to do is we'll keep on iterating in such a way that this fixity, or we are trying to adjust it in such a way that my final net moment at that joint will be 0. So 240 minus 250 is minus 10. So I'll apply a plus 10 moment there, and then I'll obtain a plus 4 and plus 6 will be my distribution factors. Then again I'll have some net moment. See, in the next step again what happened? Initially we are getting minus 10 as my net moment. In next step what I'm getting is, what is my next step? 60. So in my next step I'm getting again minus 60 as my net moment. You can see plus 60 and 0 here. So minus 60 is my net moment. So I'll apply a net moment of minus 60 to actually get my final moments as this plus this equal to 0. And then I'll keep on iterating that in such a way that my net movement. So if you see in the end, my final net movements are plus 0.01 and plus 0.005. That means it is 0, almost 0, equal to almost 0. That means it's already, now it is balanced. So that means now MBA and MBC plus MCD is going to be 0.
Okay.
Yeah, so that is how we are iterating in this. Yeah. So let us take one more question. This question we will try to solve using no. This question will try to in this question we'll try to solve a frame with a sway. Okay. Frame with a sway is the reason why I'm directly taking the frame with a sway is actually it has all different types of complications involved in this. So once if we can solve this question, I think it's easy to solve any questions on frames. Okay. Just give me a second. Yeah. So the question is something like this. We have a frame, a simple frame. Okay. And there is a point load acting 16 kilonewtons. And the load which is acting is 16 kilonewtons, and it is acting at a distance of 1 meter, and this is about 4 meters. Okay. And the length of the column or the vertical member is 5 meters. and this is 5 meters. Let me write it as AB, ABCD. Okay. So this is the question. Will it sway? Yes, it will sway because the load is unsymmetric. So it is definitely going to be sway. It is going to sway. Okay. So when you have a sway, you actually the reason why we are again discussing about the sway and non-sway is if there is no if it is not swaying, right? If it is not swaying, that means let us say I have a support, or let us say I have a pin support here, something like this. So this is simple. It is again similar to the beam. Okay, it is similar to the beam. You can just simply, it is like ABCD beam, and then you can just simply do this moment distribution method. Uh, whatever we have solved so far, and we can directly simply use that principles and we can solve it. But if you have a sway, what happens is that you will have a net horizontal forces coming in this because of the sway. We'll see why are we getting those net horizontal forces. So let us let us solve the problem, and then we'll keep on answering the questions why we are going to get the net horizontal forces. Okay. So the first step is again to find out the distribution factor. So again in this I have taken all the lengths same. So if the lengths are same, EA is same, then the distribution factors are always it is distributed uniform or equally. Okay. So I'll directly write what the distribution factors. Distribution factor for BA is equal to distribution factor for BC is equal to distribution factor for CB is equal to distribution factor for CD is equal to zero point 0.5. The reason why I'm writing B and C is the joints we will have a distribution factors. So fixed end moment. Now we also have an external load 16 kilonewton which is acting in span BC. So fixed end moment in BC is PL by 8 minus PL by 8 minus 16 by 5 by 8. Oh, 16 5 is, oh, this is, so minus 10 kilonewton meter. Am I right? No, I can't write. Okay, sorry, I can't take PL by 8. Okay, I can't take PL by 8. PL by 8 is only when we have a load which is acting at the midspan. So if it is not at the midspan, it is PAB by L square, right? So P, this is A and this is B. Okay. So that is going to be P. This is, sorry, this is PA
It's
square.
PAB square.
Yeah, PAB square. Yeah, PAB square by. So this is P. A is 1, B square is 4 square, and L square is going to be 5 square. So this is going to be, this is 16. 16 times 4 square 16, 16 256 by 25 minus 10.24 kilonewton meter. So fixed end moment of CB is again minus, this is minus, so this is plus P A square B by L square. So 16 times 1 times 4 by 5 square, 64 by 24, 6250.56 kilometer meter. Okay, so 10.24 and 2.56. So this is done, and yeah, let us directly jump into solving the moment distribution. So joint, we have joint we have joint A, joint B, joint C, and joint D. Joint A has only AB member. Joint B has two common members, which is BA and BC. Joint C is having CB and CD. Joint D has only one, which is DC. So distribution factors. Let me write down the distribution factors. There is no distribution happening here. So for BA it is zero point 0.5. For BC it is zero point 0.5. For CB it is zero point 0.5. CD is zero point 0.5, and here there is no distribution happening. What about fixed end moments? Let me just fixed end moments. BA we don't have any fixed end moments. It is zero. AB BA is also zero. BC we got something which is minus 10.24. And what about CB? CB is 2.56. Okay, and CD 0 and 0. So once we have done with the fixed end moments, now again I want to just repeat. Now you see at CB like we have 2.56, right? CD we have 0. So what is the net force? The net moment. Net moments are 2.56 only. So again that is not how it has to be, right? At joint C you should have CB plus CD, MCB plus MCD should be 0. So if you want it to be 0, then you need to apply let me first do the distribution and then we'll see what is going to happen. So for that we need to apply minus 2.56 externally. So if you want to apply minus 2.56 at joint C, that will uh, the CB will be taking minus 1.28 and the CD will be taking minus CD is going to take sorry CD is going to take minus 1.28 and CD is going to take minus 1.28. Okay. Now what similarly at joint B. Now at joint B what is happening? My BC is having minus 10.24, but BA is not BA is 0. So what is my net moment there? The net moment is minus 10.24, but it should be it should be 0. It should not be minus 10.24. So for to make it 0, I'll be applying an external moment of 10.24. Okay, 10.24 at joint B. So now my net moment will be 0 at joint B. Because of 10.24, now it will again distribute itself, right? So distribution will be zero point 0.5. So that is going to be 5.12 and 5.12 here. So once I obtained 5.12, now you have a carryover, right? Once so this BA is again because of BA, I'll have a carryover moment in this thing as minus 2.56 positive, and BC will have carryover to CB, which is 2.56, and this will carry over to this as minus 0.64, and this will carry over to CD DC. This will be minus 0.64. Now it is done. Once it is carried over, now what is my net movements again? My net movements are 2.56 plus 0. In CD we don't have any moment. So if it is minus 2.56 plus 0, it is again 2.56. So I'll apply a negative minus 2.56 at joint C. Because of applying minus 2.56 at joint C, it will distribute half moments in CB and half moments in CD. So I'll have a distribution as minus 1.28 minus 1.28 again. Okay, if this is minus 1.28 BC, right? BC and CD. Okay, CB I have. Okay, and what about CD? This is minus 1.28. Okay, so minus 1.28 and again minus 1.28. Fine. Then what is happening at B? It is minus 0.64. So if it is minus 0.64, I'll apply a positive moment of 0.64 to make the net moment 0 at that. Because of applying a positive moment of 0.64, it will distribute in BC as again 0.36 positive and BA as 0.36 positive. So BA will have a carryover factor to AB as 0.18, and you have a carryover factor from this, it is minus 0.64, and this will carry over to this as minus 0.18, and this will carry over as again minus 0.64. Okay, you'll have a distribution again. So now again the net moment at joint C, you can see here the net moment at joint C is 0.18. Let me iterate it and let me iterate. Is it 18? Yeah, 1.36. Sorry, this is 0.32. Sorry, 1616. Sorry, this is 0.32. So this is 0.16. Yeah, that's it. So I have a net moment of 0.16 coming at joint C. So I'll apply minus 0.16 to make my net moment 0 there. So if I'm applying a net moment of minus zero point 0.6 at joint C, it will distribute CA and CB and CD equally, right? So this will be minus zero point 0.8 minus zero point 0.08 minus zero point 0.08, and this is minus 0.3 0.64. So this will to make the net movements at joint B 0, I need to apply positive moment of 0.64 at that joint. So if I'm applying positive moment of 0.64 at that joint, BC will be having a distributed moment of 0.32 positive, and BA will have a distributed moment of 0.32 positive. Okay. Now the carryovers will be 0.16. So you have again 0.16 here and again 0.04 here, and then this is going to be minus 0.04. I think this is a good approximation. I think this is fine. We can stop it. You can stop, or if you want, you can further continue. But let me stop it here. So once we stop it here, what's again the reason why I'm stopping is, so you see what is happening at C, at joint C. You have 0.16 plus 0, so the net movements are 0.16. So 0.16, I'll just assume it as almost equal to 0. Okay. And in my joint BC, what's happening, my net movements are minus 0.04. So that's fine for me, because that is going to give me a good solution there. Okay. So you might be again thinking what is going to happen in the above steps, because in the above steps it's already, in these steps we have already balanced it. How we are balancing it? We are actually applying a unit rotations all sorry, applying a negative moments all the time, right? So this is already balanced in that. So no need to worry in that. We need to only worry what is happening in the carryover moments. Okay. So how do you find the final moments? The final moments are nothing but the additions of each thing. So you'll do the addition here and then you'll find out. So this is going to be 2.56 plus 0.16 plus 0.16. That is almost 2.88. What is going to happen at BA? 5.12, 0.32, 0.32, 0.64, 5.12, that is 5.78. And let us just see what is going to happen here. 5.12 minus, minus 10.24, 5.12 minus 0.64, 10. So if you just do this thing, right, you'll be getting minus 5.84. You need to consider this also. Okay. And then what is going to happen here? 2.56 minus 1.28, all these things will be equal to 2.72. And CD minus 1.28 minus 1.28, almost minus 2.56, something like that, or plus you have this minus 2.72, and this is going to be minus 1.28, 1.28, 1.32, minus 1.32. So now we have obtained the fixed end moments. Okay, we have obtained the fixed end, or the end moments in each at each joint. Okay, let me just redraw everything again. So we have obtained what is going to happen. We have understood what is going to happen at each one. So let me just draw the free body diagram. So this is my A and B. Sorry, this is my AB and CD. Okay, let me use some other. This is my A, B, C, D. Okay. Now at A, what did I obtain? I have obtained a positive moment of 2.88. So if it is positive, that means it is going to be clockwise. So 2.88. At B, BA is positive again. It is 5.78. So this is 5.78. Fine. CD. Let me just ignore CB. I'll tell you why we are ignoring CB for now. So CD. What is going to happen at CD? CD is again minus 2 point. So what does minus mean? This way, minus 2.72. And DC is minus 1.32. So minus, how do you should have? Yeah, minus 1.32. Is it 32? Minus 1.32. Yeah. Okay. So you need to keep one thing in mind, that at support A, it's a fixed support, right? You also have a horizontal reaction coming from support A and support D's, right? So let me just find out what is my horizontal reaction. So horizontal reaction, see, you can see MAB and MBA are both clockwise. So you should develop a anti-clockwise movement at this, such that it will balance it, right? So this should be in this direction. So let us call it as horizontal at A. HA is going to be 2.88 plus 5.78 divided by 5. 7 points this thing, and this should be 1.732. Sorry, 1.73. And what is going to happen here? So everything is actually rotating in this direction. So you should have a force coming in this way to actually counter and rotating this, right? So H at D is going to be 1.32 plus 2.72 divided by 5. This is 3, almost 4 by 5 is almost point 0.8. This is 0.81. Okay. Now, HA plus HD, what is how much is that? HA plus HD is going to be HA plus HD is 1.73 minus 0.81. Okay. Yeah, because HA is towards the right and HD is towards the left. So this is going to be point 72 12 9.92. Yes, 0.92 kilonewtons. So now what is actually balancing this 0.92? We don't have anything horizontally, right? We only have, see, we only have a point load which is acting on the beam BC, and that to 16 kilonewtons. But because of that, it is actually generating 0.92, which is a net force, net shear force, right? At A and D. So there must be something which is actually, which we kind of missed out, and it has to actually negate this 0.92 value coming on the shear supports, or the supports at A and D. So there comes this way, okay? So what happens is that now you have the frame, okay? This is the frame, and you, okay, this is a frame. So so far what we are actually assuming is, we are assuming that there is a horizontal, or we are actually trying to restrict this, and this restriction is nothing but 0.92. Okay, why this restriction is 0.92? Because we are getting net forces, this plus this. So this is 1.73, and this is in this direction, this is 0.81. So because of this net, there is a restriction coming as 0.92. But in the real structure, there is no restriction there, right? So in order to remove that restriction, what we actually assume is that we'll actually try to apply a force of 0.92 in this direction. Okay. So how do we apply that force of 0.92 in this direction? So again, that we'll use the same trick which we have used earlier. So what we'll try to do is, we have this support. Sorry, we have the frame, something like this. If you are applying a horizontal force of 0.92 kilonewton in this direction, the right side direction, what happens? It will sway to the right, right? So when it is swaying to the right, this will sway something like this. So this is delta, and this is delta. The reason why both are deltas, because we'll assume that there is no shear, there is no axial. The axial rigidity of BC is very too high, so that it is not deforming axially. It is just having a rigid body sideways movement. Okay. And why did I consider there is no rotation here? The rotations have not been considered here. Why? Because the rotations have already been considered while we are considering the moment distributions, right? So in that, it's already been considered. So now it is like we have done with for the thetas, the rotations, but right now we should also find out what how much the sway is or the deltas are. Okay? So if we have delta displacement towards the right, how much is the moment it is going to transfer here? If you remember, this is going to be 6 EI delta by L square. Fine. So you'll have the same 6 EI delta by L square. Mind you, this is again, this is not carryover. You can't say simply half. Why you can't say half? Because we have already solved this. So we have two supports. We have a support. We have a support settlement of delta. Support settlement of delta. This is going to induce 6 EI delta by L square here, and the same 6 EI delta by L square in this. Okay. So now that delta actually is because of that force R. Fine. So what we'll try to do is now we'll just try to play a trick. The trick is we'll try to apply a movement. So again, movement distribution is again about the movements, right? We are not at all talking anything about what is the shear forces or the joint forces or whatever the forces applied at the joints or something that no in the concepts we are not at all discussing anything about that. We are trying to actually find out what are the joint fixed end moments because of those loads, and then we are trying to iterate to find out the solutions in the moment distribution method, right? So similarly, what we'll try to do in this also, this is 6 delta by L square, right? So this is 6 by delta by L square. So let us simply assume, or let us simply say that I will apply a moment M, and I'll apply a moment of, let us say, some 100 or 50 or 1 kilometer, whatever it is. So we'll try to apply moment M. So you should be clear that MAB and MBA, MCD and MDC. Okay. So if I apply a moment M because of this delta, so I'll just say because of this delta, I'm getting a moments or the fixed end moments as M, and that M I'll just assume some value initially. Okay. For now I'll assume M as, let us say, 100 kilonewtons, 100 kilonewton meter. Once we solve the question, I think then I think it will be very clear. So why I'm assuming as M as 100 kilonewton meter. So let us say because of this delta, I'm getting a moment of M, which is actually 6 EI delta by L square. So this 6 EI delta by L square, I'm assuming it as 100 kilonewton meter. Okay. So if that is 100 kilonewton meter, again I'll just try to. So now again, see, what I'm trying to do is, initially I have solved for this thing I have solved. For this I have got some moments at support A and support B, as well as the rigid joint B and C, at the rigid joint B and C. But now what I'll try to do is, in the next step, what I will try to do is, due to the sway which is delta in the rightward direction, what are my supports because of that sway? Okay. So for that I have obtained this equation 6ei delta by L square, and this 6ei by delta by L square, initially I'll assume it as 100 kilonewtons. Let us see what's going to happen. So let me write down again joint A, we have joint B, joint C, joint D. Joint A has AB, B has BA and BC, C has CB and CD, and D is having DC. Distribution factors you already know, zero point 0.5, zero point 0.5, zero point 0.5 and zero point 0.5, and this is the same. So fixed end moments, okay, fixed end moments. So again, if you remember, previously when we have both rotations and displacements, what are we doing? First, we are rotating the joint, and then we are finding the moments, and after that we are applying some displacement, and then we are finding the moments. So then we are adding it together, right? So the same procedure here also. Initially, we have done the joint rotations or the movements where we did not consider any sway, and after that we are considering some sway in the frame, and then we are finding out. So we can simply add both the solutions, and then both solutions to get the final the initial setup. Why are we adding directly? Because again, whatever the structural answers we are doing, like we are performing in this course, it is always in the elastic limit or in the elastic range. So when the material is in elastic range, then superposition is valid. What does superposition mean? Superposition means that you can rotate and then you can displace it, and then you can find both the moments m1 and m2, and the final moments will be m1 plus m2. Okay, that is what it means. So fixed moments will be AB. You can see here AB. How much is AB? So at AB it is anti-clockwise. So this is 100. BA is going to be again anti-clockwise. So this is 100. So yeah, again all the moments are anti-clockwise moments. Whatever we are assuming, see, it is swaying towards the right. We are assuming it if it is right, you are getting a anti-clockwise movement here, right? So this is going to be AB is minus 100, BA is 100, minus 100, BC 0, CD there's no movements, but CD you have minus 100, and DC is again minus 100. What about the distribution? Now once we have minus 100, again you can see here at joint C, so this is CB, this looks like CD. At joint C, what is happening? There is a net movement of minus 100. So I need to apply a plus 100 movement at joint C. So point if I apply okay, from now onwards I'll just write plus 100 I need to apply. So if I apply plus 100 at joint C, it is going to divide between CD and CB 50-50 because it is zero point 0.5, right? Similarly at BA it is similar at BA it is the net movement. So BA plus BC is again the net movement is minus 100. So I need to apply positive plus 100 to make that net movement 0. So if I'm applying net movement plus 50, it is going to divide between BA and BC as 50 and 50. Okay, next we have a carryover. So this will be carry over to BC as 25, and this will be carry over to this as 25, and this is 25, and this is going to carry over as 25. So now it is 25, 25 everywhere. So we have again distribution. Now you check. So this is almost 25 and 0. There is nothing here. So we have a net CB and CD, right? So we have a net moment of minus 25. You need to apply. So if it is minus 25, this is going to divide it as minus 12.5 and minus 12.5. And what is happening at BC? BC again the net moment is minus 25, and this is going to divide it as minus 12.5 and minus 12.5. So you have again carryover. This will be carried over as minus 6.25. This will be carried over as minus 6.25. This is going to carry over as minus 6.25. This is going to carry over as minus 6.25. So again you have distribution same cycle going on, running. So this will be plus the plus, and this is again plus. So this is going to be minus 6 minus 3.125, minus 3.125, and this is plus 3 point is it plus, sorry, plus 3.125, and plus 3.125. Next carryover, you have half carrying, half will be carried over here. So plus 1.6, 1 point, how much is this? 1.56. Is it 1.56? Yeah, 1.56, and this is 1.56 here, 1.56 here, and 1.56 here. So you have one more step distribution. The net will be minus 1.56. You need to apply minus 1.56. So this is going to distribute among itself as let us say this is going to be distributed as minus 0.78, minus 0.78. This is minus 0.78 and minus 0.78. So you can do these steps until you get some level of accuracy. Oh, so this will have a point 339, point 39. Yeah, this is point 39, minus point 39, and minus point 39, minus point 39, so on and so forth. So let me stop at this step. So we started with 100, and we have ended up the net movement here is minus 0.39. So once you just add all the steps, right, you'll be getting your final movements. So the final movements are going to be minus 80, okay, and this is minus 60. So this I have already solved, so I'm just writing it down. So this is plus 60, and this is plus 60, minus 60, and minus 80. Okay, this is my final moments. Okay, my final moments in AB, BA, BC, CD, and so on and so forth. So now let us find what is the horizontal forces because of these moments. Okay, what are my horizontal forces because of these moments? So what happens is that, let us say this is my AB and this is my CD. D, C, A, B. So AB, it is minus 80. What does it? What does minus mean? It is in anti-clockwise direction. BC, it is again minus. So minus is again anti-clockwise. It is in 60 in this direction. DC is it? Oh, DC is also again minus. So this is in this direction 60, and DC is also in this direction 80. So what is my reaction force here? So reaction forces is in this direction, and reaction forces are in this direction, same directions, right? So HA is 80 plus 60 divided by 5. 140 by 5. 140 by 5 is how much is 140 by 5? 28. Is it 28? 28, yeah. And HD is 28 again. Now, what is my net force? HA plus HD. It is 28 plus 28. How much is that? 56 kilonewtons. Okay. So now here, now what does this actually mean is, uh, by all this, like, if you are applying 100 kilonewton, if your delta is in such a way that, okay, let me just take a new page. Let us say if you have a delta, sorry, just a second. Let us say you have a delta in this way, okay. This because of this delta, okay. This delta is actually giving you 6 EI delta by L square moments, and this 6 EI by delta square, what we have assumed is 100 kilonewtons, 100 kilonewton meter. So for moment, if it is 100 kilonewton meter, it is generating a horizontal net horizontal forces of, okay, net horizontal forces of, how much is it? 50. Net horizontal forces of 56. Okay, 56 kilonewtons. Now, for a net horizontal forces, for net horizontal forces of, initially how much we have obtained? We have obtained a net horizontal forces of 0.92. So for net horizontal force of 0.92, how much my moments are? My moments should be. For net horizontal moments, that is equal to 0.92 kilonewton. What are my moments? Okay. As we said, we are dealing with the linear problems. So if your moments are actually scaling it down, you are, if see in this, you are for 100 kilonewton meter of moment, you are getting a net horizontal of 56. For the net horizontals to be 0.92, what should be the moment? Moment should be simply the proportion, the linear proportion of it, right? So moments should be the proportion. That proportion is nothing but 0.92 divided by 56 times x, whatever it is. So at the end, what will be my solutions? My solutions will be, first I'm actually letting some sway, and then I'm applying a movement in such a way that that horizontal movement, horizontal reactions are negated. Okay, so this is my final movement. This is my final equation for the movements. So how do I write MAB? Now MAB should be, MAB is equal to, if you see my initial steps, what is my initial step? So in this, it is 2.88. This is my first step. 2.88, 5.78 minus 5.78, 2.72 minus 2.72, and minus 1.32. So now, including the horizontal sway or including the sway, what we'll be obtaining is MAB is going to be 2.88 plus MAB with the sway. How much is this? This is minus 80, right? Minus 80 times 0.92 by 56. Okay, this is what my equation should be. And the reason why I'm multiplying with 0.92 by 56 is again proportionate. I have assumed that For 100 kilonewton meter, I'm obtaining a moment of 80 in my supports. Okay, in my support reaction, as my support reactions. But that is not what I need, because that is giving me a net force of 56. I need to negate it by 0.92. If I negate it by 0.92, then I should be getting it as 0.92 divided by 56 times minus 80. So this is going to be 1.57 kilometer meter. Similarly, MBA is 5.78 plus uh, minus 60 divided. The reason, see, you can just do minus 60 plus 60, 60 minus 60 and minus 80. So minus 60 times 0.92 by 56, that is equal to 4.79 kilonewton meter. So similarly, and everything will be the same. So this step will be the same. So similarly, MBC is minus 4.79 kilonewton meter. MCB is 3.71 kilonewton meter. MCD is minus 3.71 kilonewton meter. MDC is minus 2.63 kilonewton meter. Okay, once we have obtained the final moments, maybe we can just do a cross check one. So what we'll do is we'll now have this AB, right? So what is my final MAB? MAB is 1.57 positive. So clockwise 1.57. What is my MBA? MBA is 4.79 positive. 4.79 positive. What is my MCD? MCD MCD is minus 3.71. MCD is minus, so anti-clockwise 3.71, and MDC is minus again. So again in this direction 2.63. So just let me solve for the horizontal forces again. So this is going to turn like this, and this should be in this direction. This is going to turn like this, and this should be in this direction. Okay. So HA is 1.57 plus 4.79 divided by 5. Sorry. So 1.57 plus 4. Let us just do it later. HB is 2.63 plus 3.71 divided by 5. How much is this going to be? So let me just clear out this 5. 6, 3, 12, 3, 4, 5, 6, 6.33 by 5. And this is going to be 7, 3, almost 0, 7, 6, 3, 3 to 5, 6. This is 3.71. Okay. This is going to be 6.34 by 3. So this is in positive right side, and this is going to be right leftwards. Now you can see, now you can actually appreciate HA plus HB is 0. All okay. This is 6.33 and 6.34. That is like very fluid variations. Again, this is again an approximate method, right? So that's the reason why we are taking it as zeros. So I hope now this is clear. The reason why we are taking initial net horizontal, we are not actually, we are calculating that the net force equilibrium in horizontal direction, and then doing it in vertical, and then we are doing the we are finding out the sway, and then from the sway we are finding out what is the net force because of that sway, and then we are actually proportionately dividing, sharing it with the initial values. So any doubts or any clarifications in this?
What happens if there is already a horizontal load?
So
How to
if you
calculate?
yeah, if you have an horizontal load, right, in this right now what we are doing is uh, we try to see initially in this we have obtained the net moment as the net force is minus 0.93, right? So you can see here the net force is 0.93 here. So if you have a horizontal force, let us say you have an horizontal force of 10 kilonewtons acting there, like you have a horizontal force of 10 kilonewton acting here. So in that case you'll have a net force of minus point sorry minus 9.08 kilonewton acting. Okay, so the process will be the same. Uh, Instead of 0.92, you will be actually calculating for minus 9.08 at the end. You are able to understand?
No, if it is acting at if it is acting at the mid of the column also, we have to follow the same procedure. Because that
Correct,
will be already
exactly.
considered
So
in the fixed time movements.
correct. So if we have at the mid end, right? I think mid end we need to definitely, because at the mid end we definitely have a fixed end movements, but we are actually not considering the shear forces, right? We are not considering the support reactions. I
Yeah.
mean the forces. So definitely you need to do this net forces. Similarly, you will have the same thing, but in that extra you will have an added fixed end moments also coming if there is a force which is acting at the mid spans in the columns.
Okay.
Yeah. Anything else?
Okay. No.
Okay. Fine. I think that is what I want to discuss in the today's session. So maybe in the next session, I think we'll be discussing about we'll be introducing the stiffness matrix method. So stiffness matrix method again, it's actually a foundation for all the types of analysis softwares and all the even the final element softwares. So I think by that we'll complete the course, and then maybe at the end after the 12th week we'll have 1 hour of summary session. So uh, fine, let us meet in the next class, the next session next week.